Look up tonight into the deep velvet canvas of the sky. What you see is an ancient promise, a spectacle of light. It is an inheritance of photons, a story told across eons. You see the moon, a familiar, silent companion. You see the planets, wandering points of brilliance, and beyond them, you see the stars, a glittering dust of suns. If your eyes are sharp and the night is clear and dark, you might even perceive a faint, milky band of light arcing across the heavens like a celestial river. This is our home galaxy, the Milky Way, viewed from within. It is a sprawling city of hundreds of billions of stars, and our sun is but one citizen in its spiraling arms. For all of human history, this has been our universe, a place of breathtaking density, of overwhelming population. It feels crowded, active, brimming with celestial neighbors. We have gazed upon this cosmic abundance and felt a sense of belonging, a comforting notion that we reside in a bustling cosmic metropolis, a vibrant and significant corner of the cosmos. But what if this feeling, this deep-seated intuition of our place, is an illusion? What if the shimmering lights and the galactic glow are profoundly misleading? Imagine standing in the heart of a small, isolated oasis at night. The campfires of your tribe burn brightly all around you. You feel the warmth, hear the sounds, and see the familiar faces. You are surrounded by life. It feels like the center of the world. Yet, just beyond the reach of your firelight, lies an ocean of sand, a silent, desolate expanse, stretching for thousands of kilometers. The truth of your location is not the warmth of the fire, but the vastness of the desert. A growing body of evidence, meticulously assembled over decades, suggests that this is precisely our situation on a cosmic scale. We have been gazing at our local campfires, mistaking them for the whole world. The truth, it appears, is far stranger, far emptier, and far more profound. We are living inside a cosmic void, a colossal bubble of relative emptiness, 2 billion light-years across, and for the longest time we had absolutely no idea. Our story of discovery begins not with a grand revelation, but with a humble list. In the 18th century, the French astronomer Charles Messier, a dedicated comet hunter, was plagued by a recurring frustration. He kept discovering faint, fuzzy objects in the sky that looked like comets, but stubbornly refused to move against the background of stars. To prevent himself and others from being fooled, he began to catalogue them. M1, M31, M51. He called them nebulae, the Latin word for clouds. For over a century, these celestial smudges were a mystery. They were beautiful, enigmatic, but their true nature was fiercely debated. Were they swirling clouds of gas within our own Milky Way, perhaps new solar systems in formation? Or were they something far more magnificent? Were they, as the philosopher Immanuel Kant had speculated, island universes, entire galaxies like our own, lying at unimaginable distances? This question simmered at the heart of astronomy, a grand puzzle waiting for a key. That key arrived in the form of towering telescopes built on California mountaintops, and the brilliant, patient mind of an astronomer named Edwin Hubble. In the 1920s, using the mighty Hooker telescope at Mount Wilson Observatory, Hubble was able to resolve individual stars within the Andromeda Nebula, M31. He found a specific type of pulsating star, a Cepheid variable, a kind of cosmic yardstick whose properties were already understood. By measuring its brightness, he could calculate its distance. The result was staggering. It was a thunderclap that echoed through the halls of science. Andromeda was not a cloud within our galaxy. It was nearly 1 million light-years away, a colossal island universe in its own right, and all of Messier's other smudges were likely the same. In a single stroke, the known universe exploded in size and scope. Our Milky Way was not the entirety of creation, but a single grain of sand on an infinite cosmic shore. The age of galactic astronomy had begun, and with it, the first attempts to map our new, grander cosmos. The first maps were, understandably, two-dimensional. Astronomers could pinpoint the locations of galaxies on the celestial sphere, but gauging their true distances was a monumental task. The universe appeared as a beautiful but flat tapestry. The prevailing assumption, enshrined in what is known as the cosmological principle, was that if you zoomed out far enough, this tapestry would look roughly the same everywhere. The universe, on its grandest scales, was thought to be homogeneous and isotropic, a uniform, evenly spread distribution of matter, like a fine, consistent mist. It was a powerful and elegant idea, and it was about to be proven dramatically incomplete. The next great leap required a third dimension: depth. This was made possible by studying the light from distant galaxies. Hubble had also discovered that the universe was expanding. The further away a galaxy was, the faster it was receding from us. This recession stretched the wavelengths of its light towards the red end of the spectrum, a phenomenon known as redshift. Redshift became the ultimate cosmic depth gauge. By measuring a galaxy's redshift, astronomers could infer its distance. In the 1980s, a team at the Harvard-Smithsonian Center for Astrophysics, led by Margaret Geller and John Huchra, embarked on an audacious project. They decided to systematically measure the redshifts of thousands of galaxies in a single slice of the sky to create the first meaningful 3D map of the universe. It was painstaking, laborious work conducted telescope by telescope, night after night. No one knew what they would find. Most expected to confirm the cosmological principle, to see a relatively uniform, random peppering of galaxies. What they found instead was shocking. It was revolutionary. As the data points accumulated, a structure began to emerge from the noise. It was not a uniform mist. It was something else entirely. It was a vast, interconnected network of galaxies. The first slice of their survey revealed an iconic shape, a figure that looked so much like a person that they nicknamed it the Stickman. But as they expanded their survey, a grander architecture became clear. The universe was not a fog. It was a sponge. Galaxies were not scattered randomly. They were arranged in an intricate, web-like pattern. They clumped together into colossal superclusters, dense metropolitan hubs of the cosmos. These clusters were linked by immense, shimmering filaments of galaxies, celestial highways stretching for hundreds of millions of light-years. And in between these filaments and clusters, there was something else. Something vast, dark, and startlingly empty. These were the cosmic voids. Imagine a network of soap bubbles. The galaxies and clusters exist where the bubbles meet, on the thin, luminous films of soap, and at the junctions where several bubbles connect. But the vast majority of the volume is inside the bubbles themselves. This is the structure of our universe on the largest scales. A cosmic web where luminous matter traces the boundaries of colossal, dark vacuums. The discovery of this web was a paradigm shift. It demonstrated that the universe was anything but uniform on the scales they were measuring. It had a definite, breathtaking, and entirely unexpected architecture. And with this new map, a new question arose, one both profound and personal. If this is the structure of the cosmos, then where, precisely, are we? What is our own cosmic address in this web of filaments and voids? For a long time, we assumed we were in a relatively typical part of this structure, perhaps on a filament, or on the outskirts of a cluster, a respectable cosmic suburb. The search for our true location would lead to the most unsettling discovery of all. We began by mapping our immediate neighborhood. Our Milky Way is part of a small collection of galaxies called the Local Group, dominated by ourselves and the larger Andromeda Galaxy. This Local Group is, in turn, just a small part of the Virgo supercluster, a sprawling collection of thousands of galaxies. But even this was not the full picture. In 2014, a team led by Brent Tully used the motions of galaxies to define an even grander structure. They showed that the Virgo supercluster itself is just an outlying lobe of a much larger cosmic continent, a supercluster they named Laniakea. Laniakea is a Hawaiian word meaning immense heaven. It is an appropriate name for a structure that is 520 million light-years across. and contains the mass of 100 quadrillion suns. It is a staggering celestial entity, a watershed of galaxies all flowing towards a single gravitational point known as the Great Attractor. We finally had a name for our home supercluster. We lived in Laniakea. This seemed to confirm our place in a dense, important part of the cosmic web. But a troubling discrepancy was beginning to emerge, a cosmic conundrum that didn't quite add up. The puzzle centered on one of the most fundamental numbers in cosmology, the Hubble constant. This constant measures the rate at which the universe is expanding. Determining its precise value has been a central goal of astronomy for nearly a century. The problem is, different methods of measuring it were giving stubbornly different answers. One method involves looking back at the very early universe. By studying the faint afterglow of the Big Bang, the cosmic microwave background, scientists can predict what the expansion rate should be today. This method gives a value of about 67 kilometers per second per megaparsec. But there's another way to measure it, a more direct method. Astronomers find standard candles in the local universe, like type Ia supernovae, whose intrinsic brightness is known. By comparing their known brightness to how bright they appear from Earth, we can calculate their distance with great precision. When you measure their distances and their redshifts, you can calculate the expansion rate directly. This local measurement consistently gives a higher value, around 73. This isn't a small rounding error, it is a significant, persistent disagreement. It has been called the Hubble tension, and it represents a potential crisis in our understanding of the cosmos. It suggests that either our measurements are wrong, or our model of the universe is incomplete. For years, cosmologists have searched for an explanation. Perhaps there is some new physics we don't understand. Perhaps the nature of dark energy, the mysterious force driving the expansion, is more complex than we thought. Or perhaps the solution is simpler and much closer to home. Perhaps the problem isn't with our physics, but with our assumption about our location. We assumed we lived in an average place. What if we don't? This is where the idea of the void returns to our story. A team of scientists, including Amy Barger, Ryan Keenan, and Lennox Cowie, began to investigate our local cosmic environment with unprecedented scrutiny. They analyzed catalogues of galaxies, counting them in all directions, piecing together a density map of our corner of the cosmos. Their findings, first published in 2013 and refined since, were startling. They confirmed that our Laniakea supercluster is real. But they also found that Laniakea, this immense structure we call home, appears to be located inside a region of space that is profoundly underdense. It's as if our entire cosmic continent is situated in the middle of a vast, empty ocean. This region of low density is enormous, dwarfing even Laniakea itself. It is estimated to be roughly 2 billion light-years in diameter, making it one of the largest voids ever discovered. It has been named the KBC void, after its discoverers. And we are, it seems, right in the middle of it. To be clear, a cosmic void is not a perfect vacuum. It is not devoid of matter entirely. Our galaxy exists, after all. Rather, it is a region with a significantly lower density of galaxies, gas, and dark matter than the cosmic average. Think of it in terms of population density on Earth. The global average population density is about 60 people per square kilometre, but this average hides immense variation. Manhattan has a density of over 28,000. Mongolia has a density of just 2. Our cosmic neighbourhood, it turns out, is the Mongolia of the universe. We live in the cosmic countryside, a place of profound and beautiful isolation. This discovery is not just a geographical curiosity. It has dramatic implications. It offers a stunningly elegant potential solution to the Hubble tension. If we live inside a massive underdensity, a bubble in the cosmic foam, then the physics of our local environment is different from the global average. Our void is not an island. It is surrounded by the rest of the universe, by the dense walls and filaments of the cosmic web. These surrounding structures contain immense mass, and therefore immense gravity. Imagine a raisin inside a loaf of rising bread. The dough expands everywhere, carrying the raisin with it. But now imagine that raisin is inside a large air bubble within that bread. As the dough expands, the raisin is not only carried along by the general expansion, it is also actively pushed away from the denser bread surrounding its bubble. The material on the edge of the void is pulling the material within it outwards. This creates a local additional outflow, a kind of cosmic river flowing from the center of the void. For us, here inside the KBC void, this would mean that everything around us is being accelerated away from us slightly faster than the global average expansion rate. The supernovae and other standard candles we use to measure the local Hubble constant are all caught in this same local outflow. They are being tugged on by the massive structures that lie outside our void. Therefore, when we measure their speeds, we get a slightly inflated number. We are measuring a local, provincial speed limit, not the national average. This simple, powerful idea could resolve the Hubble tension without resorting to new physics. The measurement from the early universe, the cosmic microwave background, reflects the true, global, average expansion rate of the entire cosmos. Our local measurement, from supernovae, is a biased number, skewed high by the peculiar gravitational environment of our cosmic void. The two numbers aren't in conflict. They are simply measuring two different things, the global average versus the local anomaly. The crisis in cosmology might be, at its heart, a crisis of cosmic geography. We simply misunderstood our own address. This revelation forces us to re-examine everything we thought we knew about our place. It challenges one of the most fundamental assumptions in science, the Copernican principle. Named after Nicolaus Copernicus, who showed the Earth was not the center of the solar system, this principle suggests that we do not occupy a special or privileged position in the universe. It has been a guiding light for centuries, protecting us from the arrogance of assuming we are central. But does living in one of the largest voids in the known universe violate this principle? The answer is complex. On one hand, being in the center of a giant void sounds suspiciously like being in a special place. But on the other hand, the voids are the largest components of the universe by volume. Statistically, it might be more likely for a galaxy to find itself in a void than on a thin filament or in a dense cluster. Perhaps our position is not special, but rather typical. And our previous assumption that density was the norm was the real bias, born from the simple fact that we were looking at our own local, luminous neighborhood. We were oasis dwellers, assuming the whole world was made of palm trees and water. The implications ripple outwards, even touching upon the greatest mystery of all, dark energy. This enigmatic force is believed to be driving the accelerating expansion of the universe. Our primary evidence for its strength comes from those local measurements of supernovae. But if those measurements have been skewed by our position in a void, then it's possible we have miscalculated the true power of dark energy. The acceleration of the cosmos might be less aggressive than we currently believe. Our understanding of the ultimate fate of the universe, whether it will expand forever into a cold, dark big freeze or something else, hinges on this value. By finding our true place on the map, we may be forced to redraw our predictions for the end of time itself. Let us pause for a moment and absorb the sheer scale of this reality. Our galaxy, the Milky Way, with its hundreds of billions of suns, is a mote of dust. Our supercluster, Laniakea, with its 100,000 galaxies, is a single, fragile bauble. And this bauble is suspended within a colossal sphere of emptiness, a chasm of space-time so vast that light takes 2 billion years to cross from one side to the other. We are inhabitants of the void. The light we see from the most distant galaxies has traveled across this immense emptiness to reach our telescopes, its path subtly shaped by the void's gravitational landscape. What does this mean for us? Not as scientists, but as thinking, feeling beings. Does it change how we see that velvet canvas of the night sky? There is a certain loneliness in this new picture. The sense of a bustling cosmic city is replaced by the quiet reality of a remote wilderness. The distant clusters and superclusters, the true metropolitan centers of the cosmos, are even further away than we imagined. We see their lights, like the glow of a distant city, Seen from a remote farmhouse on a clear night, they are a reminder of a grander, denser world to which we do not belong. And the future this paints is one of deepening isolation. The universe's expansion is accelerating. As time goes on, the space between everything will continue to stretch. The distant superclusters that form the walls of our void will recede from us at ever-increasing speeds. One day, they will cross a cosmic horizon, their light forever unable to reach us. The night sky of the far future will be a far emptier place. Our own local group of galaxies will have merged into one single, giant elliptical galaxy. Beyond it, there will be nothing, just an endless, featureless, starless black. The inhabitants of that distant future will have no way of knowing about other galaxies, about the Big Bang, about the cosmic web. They will be truly and irrevocably alone. Our era, with its star-filled sky, is a fleeting, precious moment. But there is another way to view this revelation. It is not a story of demotion or insignificance. It is a story of sublime discovery. It is a testament to the relentless, indomitable power of human curiosity. We are a species that evolved on the plains of Africa, our senses tuned to the scale of predators and prey, of stones and trees. And yet, from our tiny perch on this small, rocky world, we have reached out with our minds and our instruments. We have measured the trembling of space-time, captured the fossil light of creation, and charted the geography of the entire observable universe. We have discovered that we live inside an immense crystal palace of our own making, a bubble of perception built from the light of our nearest neighbors. And now we have finally stepped outside and seen the true landscape for the first time. It is a landscape of profound emptiness and breathtaking structure, of shimmering filaments laid across chasms of darkness. Our discovery of the KBC void is not an eviction from a grand city. It is a homecoming. It is the moment we finally learned the true nature of the place we were born. So look up again at that deep velvet canvas. See the stars not as a crowd, but as rare and precious jewels, scattered across an immense and silent emptiness. Feel the profound stillness of the cosmic void that surrounds you, that cradles our galaxy and everything we have ever known. There is a strange and powerful beauty in this new perspective, a humility in understanding our true, remote place in the grand scheme. The universe did not build a crowded metropolis for us. It offered us a quiet, solitary, and magnificent wilderness. And it left us with a mind capable of seeing it, of mapping it, of understanding it. Our journey to chart the great cosmic emptiness has only just begun. It begins with a whisper, not a sound that travels through air, for there was no air. It was a sound before sound, a hum of pure energy that once filled everything, everywhere, all at once. This is the oldest light in existence, a faint elegiac glow that has journeyed across the entire breadth of time and space to reach us here now. It is the universe's first message, sent only a few 100,000 years after the moment of creation itself. We call it the cosmic microwave background. For generations we have seen it as the ultimate confirmation, the unassailable proof of our cosmic origin story. It has been our map, our compass, our foundational text, the bedrock upon which all of modern cosmology is built. This radiation, this fossil light from a time when the cosmos was an infant, has been translated into a grand and triumphant narrative, the story of the Big Bang. It tells of a universe born in an incandescent flash, expanding and cooling, forging matter and energy from a singular point. The story it tells is one of impeccable, almost mathematical elegance, and for decades we believed we had heard it perfectly. But what if we have been misreading the scripture? What if hidden within this supposedly perfect echo of creation, there are notes of dissonance, subtle, disquieting patterns that whisper of a different story, a narrative far stranger and more complex than we ever dared to imagine? This is a journey into the heart of that ancient light, a quest to understand the anomalies, the glitches, the unexpected shadows that lie upon the face of the infant universe. These are the cosmic heresies, the statistical ghosts that haunt our most cherished theories, and they force us to ask the most profound and unsettling question a scientist can face. What if the foundation of everything we know is flawed? To understand the depth of this crisis, you must first understand the sheer perfection of what we found. Imagine you are an archaeologist, and for centuries legends have spoken of a single monolithic stone tablet upon which the history of the world was first inscribed. Theorists have predicted its shape, its size, even the language it might be written in, but no one has ever seen it. Then one day you unearth it, and it is exactly as the theories foretold. That is what the discovery of the cosmic microwave background felt like for the world of cosmology. It was the vindication of a bold, almost mythic idea. In the mid-20th century, two competing visions of the cosmos vied for dominance. One was the steady-state theory, an eternal, unchanging universe that had always existed and always would. It was elegant, simple, and philosophically comfortable. The other was the Big Bang, a far more violent and dramatic tale of a universe with a distinct beginning, a moment of creation from which everything erupted. This theory made a startling and testable prediction. If the universe truly began in a hot, dense state and has been expanding and cooling ever since then, the inferno of that creation should not have vanished entirely. Its embers, cooled over billions of years of cosmic expansion, should still be detectable today. They would have stretched from brilliant high-energy light into the invisible low-energy realm of microwaves. The entire sky in every direction should be filled with a faint, uniform thermal glow, the afterglow of the Big Bang itself. For years it was a ghost sought by astronomers. Then in 1964 it was found entirely by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were struggling with a persistent, inexplicable hiss in their horn antenna in New Jersey. They tried everything to eliminate it. They recalibrated their instruments, checked their wiring, and even cleaned out the pigeon droppings they thought might be the source of the interference. But the hiss remained. It was isotropic, coming from every direction with the same intensity. It did not change with the time of day or the season. It was as if the universe itself was humming a single monotonous note. What they had stumbled upon was not noise. It was the signal. It was the sound of creation. They had found the afterglow. The discovery was a death blow to the steady-state theory and a coronation for the Big Bang. The monolithic tablet had been found, and it solidified our entire understanding of cosmic history. The temperature of this background radiation was measured at just under 3 degrees above absolute zero, almost precisely what the Big Bang theorists had predicted. Its spectrum, the distribution of its energy across different frequencies, was a perfect blackbody curve, the most perfect blackbody curve ever measured in nature. This meant it could only have been produced by a system in perfect thermal equilibrium, a state the universe could only have achieved when it was incredibly hot and dense. The evidence was overwhelming. Our universe had a beginning. The CMB became cosmology's Rosetta Stone, allowing us to translate the present-day state of the cosmos back into the physics of its earliest moments. This single discovery transformed cosmology from a field of philosophical speculation into a precision science. It was a moment of profound clarity, a peak from which we could survey the grand sweep of cosmic time. We had found our origin story written in the language of microwaves, and it was beautiful. But with this clarity came a new and troubling set of puzzles. The very perfection of the CMB, its astonishing uniformity, presented a paradox that seemed to defy the laws of physics. The signal was the same temperature everywhere we looked, to a precision of 1 part in 10,000. This feature, known as isotropy, is deeply unsettling when you consider the sheer scale of the cosmos. Imagine two opposite points on the sky. Light from one of those points has only just reached us after a journey of more than 13 billion years. Light from the opposite point has done the same. This means those two regions of the early universe could never have been in contact with each other. They were separated by a gulf of space-time so vast that no signal, not even light, could have traversed the distance between them in the time the universe had existed. They were, and always had been, causally disconnected. So how did they know to be the same temperature? How did they conspire to reach a state of perfect thermal equilibrium across distances they could never have crossed? This is the horizon problem, and it was a profound crack in the foundation of our beautiful new theory. It was as if you found two people on opposite sides of the Earth who had never met or communicated in any way, yet had independently written the exact same novel word for word. It would suggest some unknown prior connection. Furthermore, there was another equally deep problem. According to Einstein's theory of general relativity, the geometry of space-time can be curved by the matter and energy within it. Our universe appears to be almost perfectly geometrically flat. This is a state of incredible balance, like balancing a pencil on its sharpest point for billions of years. Any tiny deviation from perfect flatness in the early universe would have been magnified exponentially by cosmic expansion, leaving us today in a universe that was either wildly curved into a closed sphere or a sweeping open saddle. The fact that we inhabit this knife edge of geometric balance demanded an explanation. To solve these two profound riddles, a new chapter was added to the story of the Big Bang. A chapter of such audacious scope, it still borders on the fantastical. It is the theory of cosmic inflation. Inflation proposes that in the very first fraction of a second after the Big Bang, a moment of unimaginable brevity, the universe underwent a period of hyper-accelerated expansion. It swelled in size by a factor greater than a trillion, growing from a point smaller than an atom to something larger than a grapefruit almost instantaneously. This violent, explosive growth provides an elegant solution to our problems. It explains the temperature uniformity because before inflation, the entire observable universe was once a tiny, causally connected patch. Everything was in contact, everything could reach thermal equilibrium. Inflation then stretched this smooth, uniform patch to cosmic scales, preserving its even temperature across vast, now disconnected regions. It also explains the flatness. Imagine a tiny crumpled balloon. If you inflate it to the size of the Earth, any small patch on its surface will now appear almost perfectly flat to an ant living on it. Inflation did the same to the geometry of space-time, stretching any initial curvature into a state of near-perfect flatness on the scale of our observable horizon. Inflation was a theoretical masterstroke, a concept that patched the holes in the Big Bang model with breathtaking ingenuity. But like all good scientific theories, it made its own predictions, and these predictions would demand that we look even closer at our sacred cosmic text. If inflation happened, it wouldn't have been a perfectly smooth process. In that first instant of creation, the universe would have been a sea of quantum uncertainty. Tiny random quantum fluctuations, microscopic ripples in the fabric of space-time itself would have been present. Inflation in its ferocious expansion would have grabbed these minuscule quantum jitters and stretched them to colossal astronomical scales. These stretched out fluctuations would have become tiny variations in the density of the primordial soup. Some regions would have been infinitesimally hotter and denser, others infinitesimally cooler and less dense. Therefore, the cosmic microwave background should not be perfectly flawlessly uniform. Hidden beneath its veneer of perfection should be a tapestry of minuscule temperature variations, a pattern of warmer and cooler spots reflecting those primordial quantum ripples. These tiny fluctuations, the theory predicted, were nothing less than the seeds of all future structure. The slightly denser, warmer regions would act as gravitational anchors, their gentle pull gathering more and more matter over billions of years. They were the cosmic seeds from which the first stars, the great galaxies, and the immense superclusters we see today would eventually sprout. Without these imperfections, the universe would have remained a smooth, uniform, and utterly boring soup of gas devoid of stars, planets, and life. We are here because the early universe was not perfect. Finding these predicted imperfections became the next great quest of modern cosmology. It would require technology of unimaginable sensitivity satellites, capable of mapping the entire sky and detecting temperature variations of mere millionths of a degree. 3 generations of space telescopes were sent on this holy grail mission. First came NASA's Cosmic Background Explorer, or COBE, in 1989. After years of scanning the heavens, it produced a map of the microwave sky that stunned the world. There they were. The wrinkles in time, as the lead scientist famously called them, the temperature fluctuations, the seeds of cosmic structure were real. The discovery was front-page news across the globe, hailed as one of the greatest scientific achievements of the 20th century. A decade later came the Wilkinson Microwave Anisotropy Probe, or WMAP. It mapped the sky with far greater precision, producing an image that has become an icon of modern science. That mottled oval, a tapestry of blue and red splotches representing the cool and warm spots on the infant universe, became our first detailed baby picture of the cosmos. The specific pattern of these spots, their sizes and distribution, matched the predictions of the inflationary Big Bang model with astonishing fidelity. It seemed as if the case was closed. Every new observation, every more precise measurement, only served to reinforce the standard model of cosmology. The story was complete, or so we thought. The final chapter in this observational saga was written by the European Space Agency's Planck satellite. Launched in 2009, Planck was a technological marvel designed to map the CMB with a sensitivity and resolution that dwarfed its predecessors. Its mission was to scrutinize the cosmic blueprint with an eagle eye to test the standard model to its breaking point. For years, it scanned the sky, gathering data of unparalleled quality. The scientific community waited with bated breath, expecting Planck to deliver the final definitive confirmation, to iron out the last minor uncertainties and present a flawless portrait of our cosmic origins. In 2013, the results came in, and the universe began to get strange. On one hand, Planck's data confirmed the standard model to an even more staggering degree of precision than ever before. The parameters of our universe, its age, its composition, its rate of expansion, were now known with breathtaking accuracy. The triumph was undeniable. But Planck's instruments were so sensitive, so powerful, that they saw things that weren't supposed to be there. As scientists began to subtract the model of the expected randomly distributed fluctuations from the real data, a residue remained. A set of subtle large-scale features that seemed to defy the fundamental assumptions of our entire cosmological framework. These are the anomalies, and they are profoundly, deeply weird. The most fundamental principle of the Big Bang model is the cosmological principle, the assumption that on the largest scales, the universe is homogeneous and isotropic. It looks the same everywhere, and there is no special place or preferred direction in the cosmos. But Planck's map seemed to hint at just that, a preferred direction. Across the entire sky, the hot and cold spots were not quite randomly distributed. They appeared to be subtly aligned along a particular axis, a cosmic line stretching across the universe. This alignment, nicknamed the axis of evil, for the havoc it could wreak on our theories should not exist. It was as if the universe had been subtly combed in one direction, violating its most basic symmetry. Then there was the issue of the hemispheres. When the sky was divided in two, one half appeared to have slightly stronger temperature fluctuations than the other. Our cosmic baby picture was lopsided, a feature completely at odds with the idea of random quantum-seeded beginnings. And perhaps most famous of all is the cold spot. In the southern celestial hemisphere lies a patch of the microwave sky that is inexplicably anomalously cold. It is a vast void of lower temperature, far larger and deeper than should be possible according to the random fluctuations predicted by inflation. Statistically, its existence is an extreme long shot, a 1 in 1,000 fluke, or perhaps something more. It's a chilling, empty space on the map of creation where the rules seem to have been different. For decades, we celebrated the near-perfect agreement between theory and observation. We built a towering edifice of understanding on the foundation of the CMB. Now we are forced to confront these unsettling patterns. These are not small, insignificant details. They are large-scale structural oddities that challenge the very premise of cosmic randomness and uniformity. They are the marginalia in the sacred text that seem to be written in an entirely different ink, hinting at a hidden layer of meaning we have yet to decipher. The central conflict of modern cosmology is now clear. Do we trust the overwhelming success of the model and dismiss these anomalies as statistical flukes, the cosmic equivalent of seeing faces in the clouds destined to vanish with even more data? Or do we heed their warning? Do we dare to consider that these might be the first real cracks in the monolithic structure of the Big Bang theory? Perhaps they are signposts pointing us toward a new, more profound understanding of the universe, a physics that operates beyond our current horizon. They could be evidence of a pre-inflationary past, a glimpse of whatever existed before the Big Bang. They might even be the faint, ghostly signature of other universes, the gravitational bruises left behind from a collision with another reality in the cosmic multiverse. The journey we are about to embark upon is a scientific detective story of the highest order. We will venture to the edge of time, exploring the frontier where data meets theory and certainty gives way to mystery. We will meet the scientists wrestling with these cosmic discrepancies, exploring radical new ideas that push the boundaries of imagination. We will ask what it means if our universe is not as simple, not as random, and not as elegant as we have long believed. The whisper from the dawn of time has become more complex. Within its harmonious hum, we now hear a series of perplexing, unresolved questions. The answers could either reaffirm our place in the cosmos or change it forever. The Rosetta Stone has begun to speak in a new and unfamiliar language, and we must learn to listen. What if the most profound truth about our universe was discovered not with a thunderous revelation but as an unwanted whisper? What if the key to unlocking the very beginning of time was not sought but stumbled upon an irritating and persistent hum that refused to go away? This is not a parable, but the strange and beautiful story of how we first heard the echo of creation. Our journey begins not in a gleaming modern observatory, but in the rolling hills of New Jersey in the year 1964. Here at Bell Labs, two young radio astronomers, Arno Penzias and Robert Wilson, were given a peculiar new toy, a massive horn-shaped antenna, a relic from the dawn of satellite communication. Their task was mundane, almost pedestrian. They were calibrating this sensitive instrument, preparing it to map faint radio signals from the Milky Way. But from the moment they turned it on, they were haunted. A faint, persistent noise, a low, steady hiss saturated every measurement. It was like trying to listen for a pin drop in a wind tunnel. This wasn't the crackle and pop of a thunderstorm, nor the intermittent noise from a city. This was different. It was unnervingly constant, a featureless hum that came from every direction they pointed the antenna. Day or night, summer or winter, whether aimed at the heart of our galaxy or into the deepest void between the stars, the hiss remained. It was a ghost in their machine. Their scientific minds treated it as any engineer would, an error, a flaw in the system. They spent a year waging war against this phantom. They checked and rechecked every wire, every amplifier, every soldered joint. They accounted for the ambient heat of the antenna itself, and even for the faint radio noise of our own atmosphere. Still, the signal persisted, an immutable isotropic whisper. In a moment that has become legendary in the annals of science, they climbed into the vast throat of the antenna. They were searching for any source of interference, and found a rather messy one. A pair of pigeons had taken up residence inside, leaving behind what the ever-polite Wilson would later call a white dielectric material. Could this truly be the source? Could the faint thermal radiation from pigeon droppings be the interference that was confounding their multi-million-dollar experiment? With brooms and brushes, they painstakingly cleaned the antenna, evicting its inhabitants and removing every last trace of their presence. They pointed the horn to the sky once more, held their breath and listened. The hiss was still there, unchanged, undiminished, utterly indifferent to their efforts. They had eliminated every conceivable source of noise from Earth, from their own technology, even from our own galaxy. In their exhaustive process of elimination, they were forced into a staggering conclusion. This noise was not from here. The signal, this ancient cosmic static, was coming from the universe itself. At that very moment, just 30 miles away at Princeton University, a team of physicists led by Robert Dick was on the verge of building their own antenna to search for the very thing Penzias and Wilson had just accidentally found. Dick and his colleagues were theorists, visionaries, who had gazed back into the furnace of the early universe with the power of mathematics. They reasoned that if the cosmos truly began in an unimaginably hot, dense fireball, the Big Bang, then the incandescent light from that inferno shouldn't just vanish. As the universe expanded and cooled over billions of years, that primordial light would have stretched its wavelength, elongated, its energy diluted. It would have cooled from a blistering white-hot glow into the invisible realm of microwaves, a faint thermal afterglow bathing the entire cosmos. They predicted this relic radiation would have a temperature of just a few degrees above absolute zero. When a colleague told Penzias of the Princeton group's work, a phone call was made that would forever alter our understanding of our own origins. As Penzias described the strange isotropic hiss and its measured temperature of roughly 3 Kelvin, the Princeton team knew instantly what they were hearing. They had been scooped. The echo they were preparing to search for had already been found by 2 men trying to get rid of it. This was the cosmic microwave background, the CMB. It was the oldest light in the universe, a fossil from a time just 380,000 years after the Big Bang, a time before a single star had ignited. It was the definitive, irrefutable evidence that our universe had a beginning. The discovery was a thunderbolt, effectively ending the long-standing debate with the rival steady-state theory, which proposed a universe that was eternal and unchanging. The universe was not static. It was evolving, and here in this faint hiss was its birth announcement. This discovery, however, was just the first note in a symphony that was yet to be written. The hiss Penzias and Wilson found was a single monochrome data point. It told us the universe had a hot past, but it was like trying to understand an entire world by looking at a single grain of sand. To truly comprehend our origins, we needed a map. We needed to transform that uniform hum into a picture, to survey the entire celestial sphere and see this ancient light in all its glory. This monumental task would require leaving the radio interference of Earth far behind. The age of space-based cosmology had begun, and its first great artist was a satellite named COBE, the Cosmic Background Explorer. Launched by NASA in 1989, COBE had 2 primary missions, each more profound than the last. First, it was to confirm the exact nature of this ancient light. The Big Bang Theory made a very specific prediction: the CMB shouldn't just be any random radio noise. Its energy spectrum should follow a perfect black body curve, the unique thermal signature of an object in perfect equilibrium, a state the early universe would have certainly been in. For years, COBE meticulously gathered data. The scientific community waited with bated breath. When the results were finally presented at a meeting of the American Astronomical Society, the room was stunned into silence. The data points from COBE didn't just align with the predicted black body curve, they fell on it so perfectly that it was impossible to distinguish the theoretical line from the measured data. The error bars on the measurements were smaller than the thickness of the line drawn on the graph. The standing ovation that followed was for more than just a successful experiment. It was a celebration of humanity's ability to reach across 13 billion years and take the temperature of creation itself. Yet it was COBE's second mission that would sow the seeds for both the greatest triumph of modern cosmology and its deepest, most perplexing mysteries. While the CMB was astonishingly uniform with a temperature of 725 Kelvin, no matter where COBE looked, theory demanded that it couldn't be perfectly smooth. In that primordial soup of light and matter, quantum fluctuations in the first moments of time should have created infinitesimally small variations in density and temperature. These variations, these tiny lumps in the cosmic gravy, were essential. Without them, gravity would have had nothing to grab onto. The universe would have remained a featureless, expanding haze of gas forever. But with them, gravity had an anchor. Denser regions would pull in more matter growing over billions of years into the magnificent cosmic web of galaxies, stars, and planets we see today. You, me, the Earth, the Sun, we are all the descendants of these microscopic primordial seeds. COBE's task was to find these seeds. It was an epic feat of cosmic archaeology, requiring the subtraction of all foreground light, the glow of our own Milky Way, dust between the stars, signals from distant galaxies to isolate the ancient signal from the background. After years of painstaking analysis, the team produced their masterpiece, the first all-sky map of the cosmic microwave background. And there they were, splashed across the celestial sphere, were blotches of red and blue representing tiny temperature fluctuations. They were almost imperceptibly faint variations of just 1 part in 100,000. It was like trying to spot a ripple just a few centimeters high on an ocean the size of the Earth. George Smoot, the lead scientist, famously declared, If you're religious, it's like looking at God. For scientists, it was perhaps even more profound. They were looking at the genetic blueprint for the entire cosmos. This map was a revolution, but its resolution was crude, like a blurry photograph of a masterpiece. The grand structure was there, but the fine details were missing. We needed a sharper view. And so, in 2001, we launched the Wilkinson Microwave Anisotropy Probe, or WMAP. Positioned 1 million miles from Earth, shielded from our planet's thermal glare, WMAP was COBE's high-definition successor. For 9 years, it stared into the cosmic dark, patiently charting the ancient sky with a sensitivity and clarity that was previously unimaginable. The data it sent back was a cosmologist's dream, a Rosetta Stone that allowed us to decode the universe's fundamental properties. The patterns in the WMAP data, the specific sizes of the hot and cold spots, acted as a cosmic yardstick. They told us the age of the universe with breathtaking precision, 13.77 billion years old. They revealed its geometry to be perfectly flat, meaning it will expand forever. And most startlingly, they gave us the universe's precise recipe of ingredients. The atoms that make up everything we have ever seen, touched, or measured amount to a paltry 5% of the cosmos. 27% is a mysterious invisible substance we call dark matter, a ghostly scaffolding upon which galaxies are built. The remaining 68% is even more bizarre, a phantom force called dark energy that is accelerating the expansion of the universe, pushing everything apart. This recipe, combined with the Big Bang and a theory called cosmic inflation, forms the standard model of cosmology. Known as lambda CDM, it is one of the most successful theories in the history of science. It's a grand narrative that explains how a universe born from a quantum flicker could evolve into the vast, structured cosmos we inhabit, and the data from WMAP was its crowning achievement. Every major prediction made by the lambda CDM model was confirmed by the WMAP data. The size of the spots, their distribution across the sky, the subtle polarization of the ancient light, it all matched. It was a symphony of agreement between theory and observation, a beautiful and coherent story of our universe, from its first picosecond to the present day. We had, it seemed, figured it all out, but science is a restless endeavor. Its greatest triumphs often hide its deepest puzzles in plain sight. As cosmologists celebrated the stunning success of the standard model, a few nagging oddities began to surface in the exquisite WMAP data. These were not glaring contradictions, but subtle whispers of descent anomalies hiding in the largest features of the map. When scientists analyzed the fluctuations on the grandest possible scales, the broadest, gentlest temperature variations across the entire sky, they found something strange. These largest ripples in space-time seemed unexpectedly weak, less pronounced than the nearly flawless lambda CDM model predicted they should be. Even more unsettling, these large-scale features appeared to be mysteriously aligned. There was a peculiar axis across the sky where the temperature fluctuations seemed to be organized, a preferred direction in the cosmos. This was deeply troubling. A core principle of cosmology, the cosmological principle, states that the universe should be isotropic, that it should look the same in every direction. Yet here was a potential hint of a cosmic North Star, an axis of evil, as it was provocatively nicknamed, that seemed strangely aligned with the plane of our own solar system. And then there was the cold spot, a vast, unusually empty and chilly patch of the sky, larger and colder than should be statistically likely in a random universe. At first, these were the concerns of a minority, the kind of subtle discrepancies that often appear at the limits of an instrument's sensitivity. They were easily dismissed. The scientific consensus was that these were likely statistical flukes, the cosmic equivalent of getting the same roll of the dice a few too many times in a row. Our universe is, after all, just one realization of an infinite number of possibilities. Perhaps we just happen to live in a slightly unusual one. Or maybe the thinking went the anomalies were not cosmic at all, but mundane errors. Perhaps our models of the Milky Way's foreground glow were imperfect, and we were failing to subtract it cleanly, leaving behind a faint artificial pattern. For a time, it was easy and scientifically prudent to believe these were just ghosts in the data, digital pigeons that would be cleaned away by the next more powerful experiment. We had built a magnificent cathedral of understanding, and these were surely just minor cracks in the plaster, not flaws in the foundation itself. Surely they were nothing to worry about. And so, with instruments of unprecedented sensitivity, we turned our collective gaze back to that first light. The grainy photograph from the 1,990 seconds had proven the concept, revealing the faint mottling of temperature that seeded the cosmos we know. But the whispers it captured were indistinct, like a message heard from across a vast and noisy room. To truly decipher its meaning, to read the universe's most ancient story with clarity, we needed to listen with a far keener ear. We needed a new generation of cosmic cartographers. This new era began not with a single thunderclap of discovery, but with the quiet, methodical hum of supercomputers. Launched in 2001, NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, was a marvel of engineering designed for one singular purpose: to create a map of the infant universe with breathtaking fidelity. For years, it orbited in the silent darkness, a million miles from Earth, shielded from our planet's thermal glare, patiently soaking in the faint fossilized radiation that has traveled for over 13 billion years to reach us. Its data, a torrent of numbers representing the faintest temperature variations, flowed back to Earth, where teams of cosmologists prepared to sift through it. Among them were scientists like Max Tegmark and Angelica de Oliveira Costa, physicists, who had dedicated their careers to teasing apart the universe's fundamental signals from the noise. They were not mavericks looking to overturn the established order. They were artisans of the Standard Model, seeking to refine its parameters and confirm its grand predictions with ever greater precision. The expectation was clear, a cornerstone of cosmological thought. When the new high-resolution map was finally assembled, it would show a universe of magnificent randomness. The hot and cold spots, the seeds of future galaxies and voids, should be scattered across the sky without any discernible pattern, like a perfectly shuffled deck of cards. This statistical uniformity, this isotropy, wasn't just an elegant idea. It was a fundamental pillar of the Big Bang, a non-negotiable tenet of the cosmological principle. The first WMAP data release in 2003 was a triumph. The map was stunning, a celestial tapestry woven with threads of light from the dawn of time. It confirmed the age of the universe, its composition and its rate of expansion, with an accuracy that was once the stuff of science fiction. The Big Bang model stood stronger than ever. But as scientists began to scrutinize the data, performing the exhaustive statistical checks that are the bedrock of good science, a disquieting murmur began to spread through the community. It started in the largest features on the map, the grandest ripples left over from the initial cosmic explosion. These largest scale fluctuations are known by deceptively simple names: the dipole, the quadrupole, and the octopole. The dipole is the easiest to understand, a massive hot spot on one side of the sky and a cold spot on the other, caused by our own galaxy's motion through space. It's a local effect, an artifact of our own velocity, and cosmologists routinely subtract it from the data to get a clearer picture of the primordial universe. But once it's gone, what remains should be random. The next levels of structure, the quadrupole and octopole, represent the most fundamental vibrations of the early cosmos, like the lowest notes played on a colossal instrument. Imagine the quadrupole as two broad hot regions and two broad cold regions, and the octopole as a slightly more complex 8-lobed pattern. According to theory, the orientation of these patterns in the sky should be completely independent of one another. The north pole of the quadrupole could point anywhere, and the peaks and troughs of the octopole should have their own entirely separate alignment. There was absolutely no reason for them to be connected. And yet, when physicists Kate Land and João Magejo at Imperial College London performed their analysis, they found something that seemed utterly impossible. The quadrupole and the octopole were aligned, not just loosely but with a statistical significance that was hard to dismiss. It was as if you had tossed a handful of sand into the air, and instead of scattering randomly, all the grains had inexplicably lined up, pointing in the same direction. This was the first hint of an anomaly so profound, so deeply heretical, that it was given a tongue-in-cheek name that stuck the axis of evil. The name was a playful nod to contemporary politics, but the underlying implication was anything but funny. The universe on its grandest of scales appeared to have a preferred direction. A cosmic compass needle was etched into the very fabric of space-time, a violation of the assumed isotropy that underpins everything we thought we knew. But the discovery was about to get stranger, morphing from a statistical curiosity into a full-blown crisis of Copernican proportions. Because this newfound axis, this inexplicable alignment of the largest structures in the known universe, pointed directly at us. It sliced straight through our tiny solar system. The plane defined by this cosmic axis was unnervingly close to the ecliptic plane, the very disk in which Earth and the other planets orbit the Sunday. Suddenly, we were confronted with a chilling coincidence. Was it possible that the largest features in the entire observable universe were somehow arranged in a statistical sense with respect to the orientation of our own insignificant planetary system? It felt like a regression, a retreat from 4 centuries of scientific progress that had painstakingly removed humanity from the center of the cosmos. Copernicus, Galileo, and Hubble had shown us that our planet is not the center of the solar system, our sun is not the center of the galaxy, and our galaxy is just one of hundreds of billions in a vast, indifferent universe. The cosmological principle was the ultimate expression of this mediocrity. We occupy no special place. But the axis of evil stared back at us from the dawn of time, whispering a different story. It hinted at a cosmic architecture that was somehow inexplicably oriented around our home. The immediate reaction from the wider scientific community was understandably one of extreme skepticism. The first assumption had to be that it was a mistake. Perhaps the instruments on WMAP had some unknown systematic error, or maybe the complex process of subtracting the foreground glare from our own Milky Way galaxy was flawed. Our galaxy is a brilliant source of microwave radiation, a luminous veil that must be carefully peeled back to reveal the ancient CMB light behind it. If this subtraction were done imperfectly, it could potentially leave behind residual patterns that might mimic a large-scale alignment. Teams around the world reanalyzed the data using different techniques to remove the galactic foreground. They looked for bugs in the software, for subtle biases in the detectors. Yet the signal refused to vanish. The alignment persisted. Then a decade later, the European Space Agency's Planck satellite produced its own map of the CMB. It was an instrument of even greater sensitivity and resolution than WMAP, designed to settle these brewing controversies once and for all. The Planck data was a monumental achievement, a definitive portrait of the early universe. And when the analysis was complete, the result was unambiguous. The axis of evil was still there. Planck saw the same unnerving alignment of the quadrupole and octopole, confirming the WMAP result with even higher statistical confidence. This was no longer a tantalizing hint or a potential error. It was a persistent, verified feature of our cosmos. The anomaly was real, but it was not the only ghost in the machine. As cosmologists pored over the increasingly detailed maps from WMAP and later Planck, another feature began to draw their attention, an anomaly not of pattern but of scale and intensity. In the southern celestial hemisphere, in a patch of sky within the constellation Eridanus, there was a region of unusual cold. This wasn't just another one of the millions of cooler-than-average spots that pepper the CMB map. This one was different. It was enormous, spanning 1 billion light-years across. And it was exceptionally cold, colder than almost any other spot of its size. Dubbed simply the cold spot, its existence presented a starkly different but equally profound challenge to the standard model. The Big Bang predicts a very specific statistical distribution for the temperature fluctuations in the CMB. Most spots should be of an average size and temperature difference. Extremely large and extremely cold regions are possible, but they should be exceedingly rare. To find one of this magnitude in our observable universe was, according to the simplest models, a severe statistical improbability. A team at the University of Cambridge calculated the odds. A feature this large and this cold should appear by pure chance only once in thousands or perhaps tens of thousands of universes like ours. Yet there it was, a great gaping wound in the fabric of creation. Like with the axis of evil, the first instinct was to find a conventional explanation. Perhaps there was something between us and the CMB in that specific direction, something that was distorting the light on its long journey to Earth. The leading hypothesis was the existence of a supervoid, an immense region of space extraordinarily empty of matter, a cosmic desert billions of light years across, with far fewer galaxies than the universal average. According to Einstein's theory of general relativity, the light from the CMB would lose a tiny amount of energy as it entered such a void and then gain it back as it climbed out the other side. However, due to the accelerating expansion of the universe, the void would have stretched slightly during the light's transit time. The climb out would be less energetic than the fall, resulting in a net loss of energy, making the light appear slightly cooler or redder to us. This was an elegant potential solution, a physical object that could imprint the cold signature we observed onto the CMB. Astronomers trained their most powerful telescopes on that patch of sky, embarking on colossal survey projects to map the three-dimensional distribution of galaxies in that direction. They were hunting for the supervoid, and they did find voids. The universe, after all, is structured like a cosmic web with great filaments of galaxies surrounding vast empty regions. But none of the voids they found were large enough or empty enough to account for the cold spot's extreme temperature. The integrated Sachs-Wolf effect, as the gravitational redshifting is known, could only explain a fraction, perhaps 10 to 20% of the observed chill. The vast majority of the coldness remained unaccounted for. The cold spot was not a mirage created by an intervening structure. Like the axis of evil, it appeared to be an intrinsic feature of the cosmic microwave background itself, imprinted on the universe at the moment of its birth. We were now faced with two distinct, deeply problematic anomalies. One was an issue of geometry and orientation, a grand alignment that seemed to violate the principle of isotropy and give our solar system an unnervingly special status. The other was an issue of statistics and probability, a feature so extreme it strained the bounds of credulity, defying the very randomness predicted by our theories of cosmic inflation. Separately, they were puzzles. Together, they formed a pattern of defiance. These were not the subtle refinements that scientists had expected to find with better data. They were not small adjustments to the known parameters of the cosmos. They were dissonant notes in the cosmic symphony aberrations that struck at the very heart of our understanding. They were a direct challenge to the cosmological principle, the foundational assumption that the universe on its largest scales is homogeneous and isotropic, the same everywhere and in every direction. This isn't just a philosophical preference, it's the bedrock upon which the entire mathematical framework of the Big Bang is built. The Friedmann equations, the equations that describe the expansion of our universe, work because we assume this large-scale uniformity. If the universe is not truly isotropic, if it has preferred directions or special places, then our entire model might be resting on a flawed premise. For decades, the Big Bang theory, buttressed by the discovery of the CMB, had been an unparalleled success story, explaining a vast array of astronomical observations with stunning elegance and power. But now, its most perfect piece of evidence, its smoking gun, was revealing features that the theory itself said should not exist. The whispers of imperfection had grown into a chorus of dissent broadcast across the heavens in ancient light. The universe was telling us that the story we had written for it might be incomplete, or perhaps in some fundamental way wrong. The question was no longer whether these anomalies were real. The question had become, what in the name of the cosmos do they mean? And so the cosmological community held its breath. The evidence from WMAP, a ghostly fingerprint on the universe's birth certificate, had divided the world of physics, creating a schism between those who saw a statistical phantom and those who sensed a profound, unsettling truth. The debate raged in conference halls and university corridors, a testament to the stakes involved, for what was being questioned was not some minor detail, but the very cornerstone of our cosmic creation story. The Standard Model, our magnificent cathedral of understanding, had a crack in its foundation, a flaw visible only on the grandest of scales. Was it a real structural weakness, or just a trick of the light? To settle the question, to adjudicate this fundamental dispute, humanity needed a new eye on the universe, an instrument of such precision and power that its verdict would be unassailable. We needed a cosmic arbiter, and its name was Planck. Launched in 2009 by the European Space Agency, Planck was not merely an upgrade to WMAP, it was a quantum leap in observational cosmology, a machine built to silence the noise and hear the whisper. Where WMAP had been a remarkable pathfinder, Planck was the definitive cartographer. Imagine trying to read the faint, faded ink of an ancient manuscript through frosted glass. That was the challenge. WMAP had given us a blurry but legible text. Planck was designed to wipe the glass clean, to bring every character into razor-sharp focus. Its detectors were cooled to a mere 1/10 of a degree above absolute zero, a state of cold so extreme that the atoms themselves are brought to a near standstill. This unprecedented chill was essential, for it silenced the thermal hiss of the instrument itself, allowing it to listen with exquisite sensitivity to the faint primordial glow of the Big Bang. It saw the sky not in 5 different frequencies of light like its predecessor, but in 9, providing an unparalleled ability to peel away the confounding veils of our own galaxy, the dust between the stars, the synchrotron radiation from electrons spiraling in magnetic fields, all the local noise that could mimic or mask the ancient signal. Planck was engineered to surgically remove it all, to isolate the pure, untainted light from creation's dawn. For nearly 4 years, the spacecraft scanned the heavens from its lonely perch a million miles from Earth, a silent, rotating sentinel gathering the most precious photons in existence. On the ground, hundreds of scientists across the globe prepared for the deluge. This was not a simple matter of downloading an image. It was a monumental task of data processing, a painstaking effort to transform raw telemetry into the most precise map of the universe ever conceived. They had to account for the gravitational pull of the Sun, the Moon, and every planet, each of which minutely perturbs the satellite's orbit and its view. They had to understand the intricate physics of every single one of its 72 detectors, each with its own unique quirks and personality. The pressure was immense. The community was waiting. The very nature of our cosmos hung in the balance. Would the anomalies that haunted WMAP's data simply evaporate under Planck's superior gaze, revealed as nothing more than instrumental artifacts or misunderstood galactic foregrounds? Or would they persist, solidified by this new, unimpeachable witness? It was the ultimate moment of truth, the opening of a celestial envelope containing the answer to a question that had plagued cosmology for a decade. In March of 2013, the wait was over. The first major data release was unveiled to the world, and as the new all-sky map of the cosmic microwave background materialized on screens, a profound collective silence fell. The map was breathtaking, a masterpiece of cosmic archaeology. Its detail was so fine, its precision so acute, that it resolved features of the early universe with a clarity that had once been the stuff of science fiction. It was a triumphant confirmation of the standard model in almost every respect. The specific pattern of hot and cold spots on smaller scales, the statistical properties of the ripples, matched the predictions of cosmic inflation with staggering accuracy. It was by all accounts a roaring success, a testament to human ingenuity. But then people started to look closer. They began to zoom out. They began to inspect not the fine filigree but the grand architecture of the map, and there, in the cold, hard light of Planck's unblinking eye, the ghosts of WMAP returned. And they were no longer ghosts, they were real. The first to be confirmed was the Great Cold Spot, that strange, unsettlingly vast patch of cosmic real estate, colder than any theory could comfortably permit, was not a glitch. Planck saw it without any ambiguity. In fact, the new data made the problem even worse. With its higher resolution and better noise filtering, Planck revealed the spot's internal structure. It wasn't just a simple cold basin, but a complex region, with a deeper, colder heart surrounded by a slightly warmer ring. The chances of such a feature arising from a random quantum fluctuation in the early universe, already slim, now dwindled to near impossibility. It was like finding a perfectly circular crater a mile wide in a windswept desert. While a natural origin is conceivable, its stark geometry demands a more compelling explanation. The cold spot, once a curiosity that could be dismissed as a 1-in-1,000 fluke, was now staring back at us, its existence confirmed by a completely independent superior instrument. It was a permanent, undeniable feature of our sky, a wound on the face of creation. The simplest explanation, that it was a mere statistical outlier, had been all but vaporized. The community had to face the chilling reality. Something out there, either a colossal supervoid draining energy from the light passing through it, or some unknown physics from the universe's first moments had carved this anomaly into the CMB. The mystery had not been solved, it had been etched in stone. Then came the verdict on the most philosophically troubling anomaly of all. The one so bizarre, so counter to our understanding of our own place in the cosmos, that it had been given a truly provocative name, the axis of evil. This was the observation from WMAP that the largest patterns in the cosmic fire, the grandest waves of temperature fluctuation, were not random at all. They seemed to be strangely aligned, organized in a preferred direction, a cosmic north and south imprinted on the entire observable universe. And most disturbingly, this axis of alignment seemed to point directly towards our own solar system. It was a violation of the Copernican principle, the foundational idea that we do not occupy a special place in the universe. Many physicists had desperately hoped, even assumed, that this was an illusion, a subtle error in WMAP's analysis, perhaps a contamination from our own solar system's motion that had not been properly subtracted. Planck, with its meticulous scanning strategy and advanced data processing, would surely make it disappear. The team pored over the data, analyzing the so-called multipole moments, the mathematical language used to describe patterns of different sizes on a sphere. They checked and rechecked their methods, searching for any possible source of error. The result was an electrifying shock. The alignment was still there. It was not quite as strong as seen in the WMAP data, but it was present at a level that could not be ignored, far beyond what random chance would allow. The universe's largest features, the ripples from which all galaxies would one day form, remained stubbornly correlated with the plane in which Earth orbits the Sunday. The celestial jury had returned its verdict, and it was unequivocal. This was not our mistake. It was not an error in the instrument. It was a feature of the sky. We are confronted with a disquieting coincidence of cosmic proportions. The grandest structure we can observe in the universe seems to acknowledge our tiny corner of it. The implications were dizzying. Did it hint at a flaw in our model of space-time? Was it a sign of some unknown interaction between the largest cosmic scales and our local environment? Or was it something far, far stranger? The community had no answers, only the cold, hard confirmation of a pattern that should not exist. And Planck's unsettling revelations didn't stop there. It also addressed the curious case of the missing power. According to the standard model, the universe should be a cacophony of fluctuations on all scales, like a perfectly struck drum resonating with every possible frequency. WMAP had hinted that the lowest notes, the longest wavelengths, corresponding to the largest angular scales on the sky, were suspiciously quiet, weaker than they ought to be. It was as if the cosmic drumbeat was missing its fundamental bass note. This was yet another anomaly that many believed would vanish with better data, perhaps explained away by an incomplete subtraction of galactic foregrounds. But Planck, with its 9 frequency bands, performed the most thorough cosmic cleaning in history. And when the dust settled, the silence was deafening. The lack of power at large scales was not only real, it was confirmed with excruciating precision. The data showed a clear and significant suppression of temperature variations on scales larger than about 60 degrees across the sky. The universe on its grandest canvas is smoother than our theories predict. It's a subtle point, but one with profound consequences. The mechanism that we believe generated all cosmic structure, quantum inflation, is expected to produce a specific spectrum of ripples. For it to fail so clearly at one particular end of that spectrum, the largest scales suggest that either our understanding of inflation is incomplete, or the very shape and topology of the universe itself is different from what we assume. Perhaps the universe isn't infinite. Perhaps it is finite but wraps around on itself like the surface of a 4-dimensional donut, preventing waves larger than a certain size from ever forming. Such ideas had been relegated to the fringes of theoretical physics. Now, fueled by Planck's impeccable data, they were being brought back into the mainstream discussion. Alongside this, Planck solidified the evidence for a hemispherical asymmetry. It confirmed that if you divide the sky into 2 halves, one hemisphere, on average, has slightly stronger temperature fluctuations than the other. It's as if the cosmic microwave background has a preferred direction, a hotter, more active side, and a colder, more placid one. Again, this violates our core assumption of isotropy, the idea that the universe on large scales looks the same in every direction. Individually, any one of these large-scale anomalies, the cold spot, the axis of evil, the missing power, the asymmetry, could perhaps be argued away as a statistical fluke, an unlikely but possible roll of the cosmic dice. But the arrival of the Planck data changed the entire game. This was the pivotal moment, the turning point in our story. Planck was the corroborating witness whose testimony was beyond reproach. It confirmed that these anomalies are not independent quirks. They are likely interconnected symptoms of the same underlying unknown physical principle. The hope that they were mere phantoms in the WMAP data ghosts in the machine was definitively extinguished. Planck, the ghost hunter, had arrived at the haunted house, turned on all the lights, and found that the ghosts were not only real, but they were sitting in the living room waiting for us. The problem was no longer one of observation or instrumentation. It was now a profound and urgent problem of theoretical physics. The standard model of cosmology, for all its spectacular successes in describing the universe on small and medium scales, was now undeniably, demonstrably incomplete when confronted with the full panorama of the cosmos. The beautiful, simple picture of our universe was beginning to fray at the edges. The anomalies were no longer anomalies. They were now established facts. They were clues, perhaps the most important clues we have ever been given, pointing towards a new, deeper understanding of the universe. They forced us to ask questions that were once considered heretical. Is the universe truly the same in all directions? Was the Big Bang more complex than we ever imagined? Is there new physics at play on cosmic scales that we have yet to even dream of? Planck had not provided the easy resolution everyone had hoped for. Instead, it had taken a series of puzzling whispers and amplified them into a clear, insistent siren call. A call that told us that the cosmos is subtly, fundamentally stranger than our best theories had predicted. The era of dismissal was over. The era of explanation had to begin. The die, it seemed, was cast. The anomalies were not ghosts in the machine, not smudges on the cosmic lens, not phantom signals from our own bustling galaxy. They were real. With this stark and unsettling confirmation, a profound silence fell over the cosmological community, the kind of quiet that precedes a storm. For decades we had held a map of the infant universe, a triumphant testament to our theories, our predictions, our understanding of cosmic origins. But now, as scientists looked closer, they saw dragons in the margins, features that had no right to exist, drawn in an ink that was not our own. The age of certainty was over. The age of frantic, brilliant, and terrifying speculation had just begun. The first casualty in this new intellectual war was comfort. The lambda-cold dark matter model, our standard model of cosmology, was more than just a theory. It was the bedrock of our cosmic perspective for a generation. It had predicted the universe's expansion, the existence of dark energy, and the precise pattern of fluctuations in the cosmic microwave background with breathtaking accuracy. It was a masterpiece of theoretical physics, a beautiful and coherent story of our universe from its first picosecond to the present day. At the heart of this elegant model lies a single, powerful and deeply philosophical assumption, the cosmological principle. It declares that the universe on its largest scales is both homogeneous and isotropic. In other words, it has no special places and no special directions. Your view from any galaxy should be roughly the same as the view from any other. It is a universe of profound democratic simplicity, but the axis of evil was a dagger pointed straight at the heart of that principle. This bizarre, inexplicable alignment of the largest patterns in the ancient sky suggested the universe did in fact have a preferred direction, a cosmic grain, a celestial north pole written into the fabric of space-time itself. It was as if the entire cosmos was subtly tilted, an observation that lambda CDM in its purest form simply forbids. The model has no mechanism, no parameter, no conceivable variable that could produce such a grand overarching structure. To lambda CDM, this axis is a statistical impossibility that just happens to be staring us in the face. It demands an explanation that the theory itself is fundamentally incapable of providing. It suggests that the universe is not as simple, not as uniform as we had so desperately wanted to believe. Then there was the cold spot, that colossal void in the cosmic heat. Our standard model explains temperature variations as the result of quantum fluctuations in the primordial soup magnified to cosmic proportions. These fluctuations should follow a predictable statistical pattern, a bell curve of probabilities. There should be hot spots and cold spots of varying sizes, but none should be too extreme. The great cold spot, however, is a wild outlier. It is too big, too deep, and too empty to be a product of random chance within the standard framework. Trying to generate such a feature in our computer simulations of a lambda CDM universe is like rolling a pair of dice 1,000 times and having them come up snake eyes every single time. You might conclude you have extraordinarily bad luck, or you might start to suspect the dice are loaded. The standard model insists the dice are fair. The cold spot screams that they are not. The model was failing not in the fine details, but in its most fundamental predictions about the character and structure of our cosmos. The great gravitational scaffolding we had built to understand everything was groaning under the weight of these impossible facts. We were no longer just refining a map. We were being forced to consider that the map, and perhaps the entire globe it was printed on, was fundamentally wrong. The downward path of conventional explanation had hit a dead end, a sheer cliff face with no handholds. To proceed, cosmology had to do what it does best in a crisis. It had to get radical. If the problem lies with the very first light, perhaps the solution lies in the very first moments. Before the flash of the Big Bang cooled into the afterglow, we now see the universe underwent a period of truly astonishing expansion, an event we call inflation. In a fraction of a second, a region smaller than a proton ballooned to a scale larger than our entire observable cosmos. This is the mechanism that smoothed out the universe, making it flat and uniform, and it's the process that magnified tiny quantum jitters into the seeds of all future structure. The standard model of inflation is simple, a single smooth field driving this exponential growth. It's like a perfectly manufactured piston pushing the universe outwards with uniform force in all directions. But what if it wasn't perfect? This became the first and perhaps most conservative of the new radical ideas. What if the inflationary engine stuttered? Imagine a tiny flaw in the process, a brief moment where the energy driving inflation wasn't perfectly smooth. Perhaps another quantum field, an uninvited guest at the cosmic dawn, momentarily interfered with the main inflationary process. This could create a dent in the expanding fabric of space-time, a region that inflated just a little bit less than its surroundings. Such an event would leave a permanent mark, a colossal underdense region in the primordial plasma. As the universe evolved, this region would naturally become a cold spot in the cosmic microwave background, a fossilized record of that initial hiccup. This idea of non-standard inflation opens a Pandora's box of possibilities. Instead of one smooth process, perhaps inflation was a chaotic multi-stage affair. Imagine not a single piston but a complex engine with multiple moving parts. Some theories propose curvaton fields, secondary energy fields, that were bystanders during inflation, but then dumped their own energy into the universe, creating additional large-scale patterns and temperature fluctuations. These could, in principle, be tuned to create something resembling the cold spot. Others suggest that the very landscape of potential energy that inflation rolled across wasn't a simple smooth slope, but a complex mountain range with valleys and bumps. Our universe might have briefly gotten stuck in one of these valleys before continuing its roll, an event that could impart a lasting asymmetry, a preferred direction onto the cosmos, a potential origin for the axis of evil. These theories are tantalizing because they don't require us to throw away the entire Big Bang model. They are more like modifications, addendums to the story we already know. They suggest that the birth of our universe was simply more complicated, more messy than our simplest models had assumed. It's like discovering a famous painting has a hidden layer underneath, revealing the artist's initial rougher sketch of their masterpiece. But there is a profound danger here. With enough new fields, enough new parameters, a theorist can explain almost anything. It becomes a game of cosmic fine-tuning where you invent new physics specifically to paper over the cracks in the old. The challenge is to create a model of non-standard inflation that not only explains the anomalies, but also makes new testable predictions. Without that, we are not doing science. we are simply telling a more elaborate story. The search was on for a theory that was not just possible but necessary, a theory that felt less like an apology and more like a revelation. When the simplest fixes to the story fail, you must begin to question the stage itself. For centuries, our geometry has been Euclidean, our space assumed to be a simple, infinite flat sheet. This is the universe of our intuition. But Einstein taught us that space is not a passive backdrop. It is a dynamic entity that can bend and warp. What if it also possesses a hidden global structure? What if the very shape, the topology of the universe is far stranger than we imagine? This line of inquiry leads us to one of the most mind-bending concepts in all of cosmology, the idea that the universe might be finite but have no edge. Imagine you are an ant on the surface of a donut. You can walk in any direction and you will never fall off an edge. You will simply walk forever, eventually returning to your starting point. To you, the world might seem infinite, yet it has a finite surface area. Now scale that up to 3 dimensions. Cosmologists began to seriously entertain the notion that our universe could be a 3-dimensional torus, a cosmic donut. If you were to fly your spaceship in one direction long enough, you would not reach the end of the universe. You would simply emerge on the opposite side, reappearing where you began. What would such a universe look like from the inside? It would be like standing in a celestial hall of mirrors. The light from distant galaxies wouldn't just travel to us once, it would wrap around the entire cosmos, reaching us from multiple directions. When we look at the cosmic microwave background, we believe we are seeing a spherical shell of light that surrounds us, the surface of last scattering. But in a finite toroidal universe, this sphere would wrap around and overlap with itself. The patterns we see on one side of the sky could be intricately linked, or even be mirror images of patterns on the opposite side. The universe would be endlessly repeating itself. Suddenly, the anomalies begin to look less like flaws and more like clues. In this Hall of Mirrors model, the strange alignments of the axis of evil might not be a special direction in space, but a consequence of the universe's fundamental repeating geometry, the axis along which the cosmic wallpaper pattern is laid out. And what of the cold spot? In some topological models where the universe is shaped like a horn or a more complex manifold, the sphere of last scattering would intersect itself in a complex pattern of circles. These circles in the sky would have identical temperature fluctuation patterns, a definitive smoking gun for a finite cosmos. The cold spot could be the result of a particularly unfortunate overlap, a place where multiple cooler regions of the primordial plasma are superimposed from our perspective. The search for these repeating circles in the Planck data has been one of the most intense efforts in modern cosmology. To find them would be to prove in one spectacular stroke that the universe is not infinite. It would give us the literal size and shape of our entire cosmos. We would have discovered the very architecture of reality. So far, the search has been inconclusive, the signals too faint, too muddled by galactic noise. But the possibility remains intoxicating. It suggests the anomalies are not a sign that our physics is wrong, but that our most basic assumption about the arena of existence, that it goes on forever, is mistaken. It is a hint that we may live inside a finite, magnificent, and intricately folded cosmic cathedral. But there is another path, a darker and more speculative road. It begins with a question that feels more like science fiction than academic theory. What if the anomalies are not features times of times our universe at all? What if they are evidence times of another times? This is the gateway to the multiverse. For many physicists, the multiverse is not a wild fantasy, but a logical consequence of our leading theories, including both string theory and eternal inflation. In this grander vision, our Big Bang was not a unique event. It was just one of an infinite number of bubble universes, each nucleating out of a turbulent, ever-expanding metaspace, a cosmic foam of realities. Each bubble could have different laws of physics, different fundamental constants, a different number of dimensions. Most would be sterile, dead universes. But some, like ours, would have the precise conditions for complexity, for stars, for life to emerge. In this breathtaking and terrifying framework, the cold spot is reimagined not as a feature from our own cosmic dawn, but as a scar. It is a cosmic bruise, the faint, lingering signature of a collision between our infant bubble universe and another, an impact that occurred in the first fleeting moments of time. The violence of this encounter would have sent shockwaves through our primordial plasma, pushing energy and matter out of the impact zone, leaving behind a vast region of lower density and temperature. This void, this cosmic contusion, would then be stretched by inflation to the gargantuan scales of the cold spot we see today. It would be the fossilized evidence of an inter-universal fender bender, a whisper from a parallel reality. The implications are almost too vast to comprehend. If this hypothesis is correct, then by studying the precise shape and temperature profile of the cold spot, we could potentially learn about the physics of the universe next door. We would be doing a kind of cosmic archaeology on an event that predates our own space-time. This idea pushes science to its absolute limit, to the very boundary of what we can test and what we must simply infer. It is profoundly controversial, decried by some as untestable metaphysics. How can you prove the existence of a place you can never visit, a reality you can never touch, and yet the anomaly in our sky persists cold and silent, and the multiverse hypothesis provides a chillingly direct, if unproven explanation for its existence? It forces us to confront the possibility that the most significant features in our sky are not about us, not about our universe, but are merely the faint residual echoes of events on an unimaginably larger stage. There is, however, one final avenue of exploration, one that brings us back from the multiverse and into the crucible of our own universe's birth. It too relies on exotic physics, but not of other universes, but of the very substance of our own. The early universe was a place of unimaginable energy and density, a state so extreme that the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, were believed to be merged into a single unified superforce. As the universe expanded and cooled, this symmetry broke. The forces we know today froze out from this unified state one by one in a series of cataclysmic phase transitions. We see analogies for this in everyday life. When water freezes, it undergoes a phase transition from a disordered liquid to an ordered crystal ice. But this process is rarely perfect. Flaws can get locked into the crystal structure, cracks boundaries where different ice crystals meet at odd angles, or trapped air bubbles. Many physicists believe that similar imperfections could have been locked into the fabric of space-time itself during the phase transitions of the early universe. These are known as cosmic defects. They would be titanic structures made not of matter, but of pure, concentrated primordial energy remnants of that earlier, more symmetric state of the cosmos. Depending on how the symmetry broke, different kinds of defects could have formed. There could be one-dimensional cosmic strings infinitely long and thinner than a proton, yet possessing the mass of a mountain range per inch. There could be two-dimensional domain walls, vast membranes of energy that could stretch across the entire observable universe. And there could be complex, tangled textures where the fabric of space-time itself is knotted and twisted. The existence of these defects is a direct prediction of many grand unified theories that seek to unite the forces of nature. Finding one would be monumental confirmation of physics far beyond our standard model. And what would one of these cosmic relics do if it crossed our line of sight to the early universe? A cosmic string, for instance, would warp the space-time around it so intensely that it would slice through the cosmic microwave background, light, creating a sharp, linear discontinuity in temperature A. Line of cosmic pixels all shifted in the same way. A cosmic texture, a vast and complex knot of energy, could unravel in a violent event, sending out a spherical shell of distortion that would leave behind a distinct hot or cold spot on the CMB. The great cold spot in this picture could be the signature of the collapse of one of these ancient universe-spanning defects. It would be a piece of cosmic scar tissue, a direct wound in the sky left over from the violent, formative moments of creation. Like the other theories, this one remains on the fringes, its predictions not yet definitively matched by the data. But it offers a powerful vision that the flaws in our perfect picture of the dawn are not flaws at all, but windows into an earlier, wilder, and more violent epoch than we ever dared to imagine. So the battle lines were drawn. On one side, the defenders of the standard model struggling to explain away the anomalies as a statistical fluke of cosmic proportions. On the other, a vibrant, chaotic rebellion of new ideas, each more radical than the last. a flawed inflation, a finite universe, a collision with another world, a scar from a cosmic defect. Each of these theories carried a profound implication, a fundamental rewriting of our cosmic story. They were all brilliant, all compelling, and all for the moment unproven. The scientific community found itself adrift in a sea of profound uncertainty, the old comfortable shoreline of Lambda CDM having receded from view. The anomalies had shattered the peace. Now they were forcing a choice. But how do you choose between such fantastic possibilities? How do you test a theory whose main events happened 13.8 billion years ago, or even outside of our reality altogether? The challenge was no longer just to theorize, but to find a new way to see, to uncover a new piece of evidence from the celestial crime scene that could turn one of these wild speculations into established fact. And so we stand at a precipice, staring into the faint mottled glow of creation itself, and find it staring back with an unnervingly intelligent gaze. The map of the infant universe, a testament that was supposed to confirm our neatest theories, instead presents us with a set of cosmic heresies, an axis of evil, a cold spot of impossible emptiness, a universe seemingly divided against itself. The beautiful simplicity of the Big Bang model, our most profound story of origins, appears to be fraying at its largest, most magnificent scales. For many, this would be a moment of crisis, a signal that our grand cosmological cathedral is built on a foundation of sand. But for science, this is not a crisis. This is a call to adventure. What follows a discovery like this is not a quiet retreat into dogma, but an explosion of intellectual creativity, a furious mobilization of the world's sharpest minds, each one drawn to the puzzle presented by that ancient light. The anomalies, far from being dismissed, have become the most fertile ground in modern cosmology, the place where the next great revolution may be seeded. The battlefield for this new understanding is not fought with telescopes alone, but with the most powerful tools of logic and mathematics we can devise. The first line of attack is not to rewrite the laws of physics, but to interrogate the messenger itself, the data. Could we have simply been fooled by chance? Is the universe a cosmic casino and we just happen to witness an incredibly unlikely but ultimately meaningless roll of the dice? To answer this, cosmologists have unleashed an arsenal of advanced, statistical methods pushing the boundaries of what we can infer from a single precious sky. You see, establishing that something is anomalous is a profoundly difficult task. It's one thing to spot a face in the clouds, it's another entirely to prove the cloud was deliberately shaped that way. Scientists must grapple with something called the look elsewhere effect. If you search through trillions of data points for any strange pattern at all, you are almost guaranteed to find one purely by accident. The challenge is to determine with rigorous certainty whether the patterns in the CMB are genuine features of the cosmos or just such a phantom. They do this by creating tens of thousands of simulated universes inside supercomputers. Each simulation is a perfect textbook, Big Bang universe allowed to evolve according to our standard equations. These digital cosmos are born, they expand, they cool, and they generate their own cosmic microwave background radiation. We then ask the computer a simple question: out of 100,000 perfect randomly generated universes, how many of them accidentally produce a cold spot as large and empty as ours? How many by sheer coincidence develop a preferred direction, an axis of evil? For years the answer hovered in a frustrating grey area. The alignment seemed unlikely, perhaps a 1 in 1,000 chance. The cold spot was more stubborn, maybe a 1 in 50 fluke. These are odds that make you sit up and pay attention, but they aren't quite the 5 sigma gold standard of discovery, the 1 in 3, 5 to million certainty that physicists demand before claiming a new particle, or force. The jury was hung. This is where new frameworks like Bayesian analysis enter the fray. Instead of just asking, how likely is this to happen by chance, this approach allows scientists to ask a more nuanced question. Given the anomalies, we see how much more likely is one theory of the universe compared to another. It is a way of weighing evidence, of letting the data itself guide us toward the most plausible explanation, even if that explanation is strange and new. This ongoing statistical war is a silent, epic struggle fought in lines of code and on supercomputer clusters. It is the bedrock of discipline upon which all the more exotic theories must be built. If the anomalies can be explained away as a statistical ghost, the story ends here. But with each new analysis, with ever more precise data from the Planck satellite, the ghosts have refused to be exorcised. They seem to be real, persistent features of our sky, demanding a physical explanation. And so, we are forced to climb the ladder of speculation, moving from the familiar ground of our standard model to the dizzying heights of new physics. The first rung on this ladder involves not shattering our existing theories, but creatively remodeling them. Perhaps the Big Bang wasn't quite the perfectly smooth, uniform event we imagined. Our current model relies on a period just fractions of a second after the beginning called inflation, a moment of hyper-accelerated expansion that stretched a microscopic universe into a cosmos of astronomical size. It was this process that is thought to have smoothed out the universe, giving us the near-perfect uniformity we observe. But what if inflation wasn't so simple? What if the field of energy that drove it was more complex, containing multiple moving parts? Theoreticians now propose models of anisotropic inflation, where the universe didn't just expand, but expanded preferentially in one direction, for a fleeting moment at the dawn of time. Imagine a balloon being inflated, but for a split second one side of it bulges out faster than the rest before settling down. That initial asymmetry, though infinitesimal, would be stretched across the entire observable universe. It would leave an indelible imprint on the largest scales, a subtle temperature gradient, a preferred direction written into the fabric of space-time itself. In this view, the axis of evil is not some mystical alignment but a fossil. It is the preserved memory of the universe's very first moment of imperfection, a directional signature from the engine of creation. This is an elegant solution as it keeps the core successes of the Big Bang and inflation intact while accommodating the strange, large-scale behavior. It suggests our universe is not fundamentally broken, just that its birth was a bit more chaotic than our simplest models had assumed. Another path explores a different kind of primordial force. We live in a universe filled with magnetic fields, from the tiny fields that make a compass work to the colossal ones that thread through entire galaxies. What if the universe itself was born with a vast primeval magnetic field, a faint but cosmos-spanning field generated in the fiery plasma of the Big Bang could have subtly herded the charged particles in the early universe? This cosmic magnetic web would have gently influenced the way light propagated, creating faint patterns and alignments in the CMB that persisted for billions of years. It could provide a physical framework for the strange correlations seen by cosmologists, a hidden order guided by a force we understand, but whose origins at a cosmic scale remain a mystery. These ideas are compelling because they are testable. More complex inflationary models and primordial magnetic fields predict other, more subtle signatures in the CMB's polarization, the orientation of the light waves. Future experiments are being designed right now to hunt for these specific fingerprints, to determine if these conservative yet revolutionary ideas hold water. But what if the truth is not a modification but a complete departure? What if the anomalies are not a feature times our universe, but a sign of something times beyond times it? This is where we take a deep breath and leap off the deflation cliff of conventional cosmology into the breathtaking abyss of the multiverse. The cold spot, that gaping void in the cosmic dawn, becomes the centerpiece of this radical new vision. One of the most captivating, if speculative, explanations proposes that the cold spot is nothing less than a bruise, a cosmic contusion left behind from a collision between our universe and another. In this scenario, our cosmos is just one bubble in a vast, frothing sea of other bubble universes, each with potentially different laws of physics, each expanding and evolving in a grand cosmic foam. Occasionally, two of these bubbles might drift too close and gently collide. The impact would not be a cataclysmic explosion, but a colossal shockwave of energy that would ripple through our infant universe. This wave would push energy and matter out of a vast region of space, leaving behind an area that was emptier and colder than its surroundings. As our universe continued to expand, This primordial scar would expand with its stretching into the enormous billion light-year wide void that we now call the cold spot. It's a staggering thought that one of the most prominent features in our sky could be the ghostly fingerprint of another reality, a shadow cast from a neighboring cosmos that we can never visit or see directly. This is not science fiction. Physicists are developing mathematical models of these collisions, predicting the precise shape and temperature profile of the scar they would leave behind. The evidence is tentative debated, but the Planck satellite data has shown that the cold spot has a sharper edge and a deeper profile than a simple quantum fluke ought to. It looks for all the world like the remnant of a violent external event. An equally mind-bending proposal suggests the problem is not with the universe's history, but with its very shape. We assume the universe is infinite and flat, stretching on forever in all directions, but that is an assumption, not a proven fact. The geometry of space-time could be far stranger. Imagine you lived inside a video game like Pac-Man. If you travel off the right edge of the screen, you don't fly into infinite blackness. You simply reappear on the left. Your universe is finite, but it has no boundary. Now imagine this in 3 dimensions. The universe could be shaped like a donut, or a more complex multi-dimensional crystal. It could be finite, wrapping back around on itself on a scale larger than we can currently see. If this were true, it would create a cosmic hall of mirrors. The light from a distant galaxy could travel across the universe and wrap all the way around, allowing us to see it in 2 different parts of the sky at 2 different points in its life. The patterns in the cosmic microwave background would do the same. The temperature fluctuations from one region would be mirrored and repeated in another. Certain patterns, certain alignments would be locked in by this repeating geometry. Could the axis of evil be an illusion born of this cosmic topology? Are we seeing the same fundamental patterns over and over again reflected by the curved funhouse mirror of space-time, creating an artificial sense of alignment where none truly exists? This theory too makes specific predictions. A finite repeating universe would generate very specific overlapping circles in the CMB map, where the patterns should be identical. Searches for these circles of repetition have so far been inconclusive, but the hunt is far from over. It is a direct test of the very fabric and form of reality itself. Finally, we arrive at perhaps the most profound and philosophically shattering idea of all, one that comes from one of the titans of modern physics, Sir Roger Penrose. His theory of conformal cyclic cosmology proposes that the anomalies are not echoes from the beginning of times our times universe, but are in fact ghosts from a universe that existed times before times ours. In Penrose's vision, the Big Bang was not a singular beginning but a transition. He argues that our universe will continue to expand, becoming ever colder and emptier, until eventually, after an almost unimaginable length of time, it is populated only by photons and other massless particles. At this point, the concepts of time and distance become meaningless, and this empty, cold future universe becomes mathematically identical to the hot, dense state of a Big Bang, and so it triggers another one. Our universe in this view is but one aeon in an infinite cycle of cosmic death and rebirth, but the transition is not perfect. Information, or rather the gravitational energy from the previous aeon, can leak through. Penrose argues that the gargantuan black holes from the previous universe, as they evaporated over trillions of years, would have released their immense energy in bursts of gravitational waves. These waves would survive the cosmic rebirth, imprinting themselves onto our own CMB as concentric circles of slightly warmer or cooler temperatures. And the cold spot, it could be the lingering gravitational echo of a supercluster of galaxies from the universe before our own. We are seeing quite literally the ghosts of a former cosmos. This is cosmology at its most daring, connecting the ultimate future of our universe with its distant past, suggesting our entire existence is just one chapter in an eternal cosmic story. Here, in this maelstrom of ideas, is where the scientific process truly shines. We have not one answer but a dozen, ranging from the conservative to the wildly speculative. Each of these proposals, anisotropic inflation, cosmic magnetic fields, multiverse collisions, a finite cosmos, a cyclical history, is more than just a good story. Each one is a concrete scientific model, a mathematical framework that makes unique, testable predictions. They are not articles of faith, they are hypotheses awaiting judgment, and that is the true gift of the anomalies. They have shattered the comfortable consensus and forced us to be creative, to be brave, to imagine possibilities about the nature of reality that we would have otherwise never dared to consider. They are the grit in the oyster that may yet produce a pearl of immense value, a new, more complete understanding of the cosmos. The fierce intellectual struggle to explain them is not a sign of a theory in its death throes, but of a science that is vibrantly, wonderfully alive. It has pushed our statistical tools to their limits, it has forced us to refine our most successful theories, and it has opened the door to entirely new paradigms. The question is no longer just what are these flaws, but what are they trying to tell us? To find that answer, we cannot simply keep reanalyzing the old map. We need to draw a new one, with new instruments, new technologies, and a new generation of explorers ready to venture into this uncharted territory. We need to build the machines that can finally put these extraordinary ideas to the ultimate test. And so we find ourselves back where we began, staring into the fading firelight of creation. This is no longer the simple uniform afterglow that Penzias and Wilson stumbled upon. It is not even the beautifully mottled map that Kobe first revealed to a waiting world. What lies before us, now etched into the fabric of space-time by the Planck satellite, is a masterpiece of cosmic cartography, a portrait of the infant universe so exquisite, so detailed, that it has become both our greatest triumph and our most profound challenge. We have journeyed from a faint, persistent hiss in a radio horn in New Jersey to this, the cosmic Rosetta Stone, a pattern of light containing the genesis of everything we see and perhaps the seeds of everything we are. For decades, this map has been the bedrock of modern cosmology. Within its subtle variations of temperature, we have read the story of our universe. We have confirmed with breathtaking precision a narrative of cosmic inflation, a violent, unimaginably brief hyper-expansion that smoothed out the universe, and yet through quantum jitters seeded the tiny density fluctuations that would one day grow. They would blossom into the first stars, the first galaxies, and eventually into us. This standard model of cosmology, our LCDM model, is an intellectual monument. It is a testament to the power of human reason to reach across 13.8 billion years and piece together a coherent, mathematically elegant, and powerfully predictive story of our origins. It accounts for the darkness between the stars, the grand cosmic web of galaxies, and the accelerating expansion of the universe itself. By all rights, this map, this echo of the Big Bang, should have been its final glorious confirmation, and in so many ways it was. The statistical properties of these hot and cold spots, their sizes, their distribution, match the predictions of our best theories to an astonishing, almost unnerving degree. It felt like we were on the verge of closing the book, of finally understanding the grand architecture. But science is not a story that seeks a final page. Its narrative thrives not on confirmation but on confrontation. And as we looked closer, as our instruments became sharper and our analysis more sophisticated, we began to notice things that did not fit, things that should not be there. It is in the grandest works of art that the smallest imperfections draw the eye, and so it is with this, the grandest canvas of all. These are the anomalies we have explored together. The great gaping cold spot, a void of unusual emptiness and chilling temperature, a feature so statistically improbable it has been called a 1 in 1,000 fluke. Is it merely an extreme statistical outlier, the universe rolling loaded dice, or is it something more tangible, more terrifying, the scar of a collision, a cosmic bruise left by another bubble universe bumping against our own in the churning, infinite foam of a multiverse we can only imagine? The very thought is staggering. It would mean that our entire universe, everything we have ever known or will ever know, is but one island in an endless cosmic ocean, and that this map carries the first physical evidence of a shore beyond our own. Then there is the alignment, the so-called axis of evil, a name born of scientific frustration for a mystery that cuts to the very heart of our assumptions. We have long held to the cosmological principle, the idea that the universe on its largest scales is the same in all directions, that there are no special places, no preferred axes. It is a principle of cosmic modesty. And yet in the very first light we see a pattern. The largest, most foundational ripples in the cosmic microwave background seem inexplicably aligned with each other, and more unnervingly still with the plane of our own solar system, the path the Earth takes around the Sunday. It whispers of a cosmic conspiracy, a connection between our local neighborhood and the grandest structures of the universe that makes no physical sense. Is it a cruel statistical trick, a once-in-an-eternity coincidence that just happens to be observable by the one species that would be troubled by it? Or does it hint at a flaw in our understanding of cosmic geometry itself, a deeper structure, a hidden grain in the wood of space-time that we never suspected? Perhaps our models are too simple, our assumptions too clean. Perhaps the universe is not as isotropic as we have so fervently wished it to be. And layered on top of this, the unsettling hemispherical asymmetry. One side of the sky, one half of this baby picture of the cosmos, is subtly but undeniably rougher than the other. The temperature fluctuations are slightly stronger, the pattern more pronounced. It is as if the inflationary energy that drove the Big Bang was not perfectly uniform, as if the cosmic furnace had a draft blowing from one side. This discovery challenges the very engine of our creation story. Inflation was conceived to explain the incredible smoothness of the universe. How then can the process that was meant to create uniformity have baked in such a large-scale primordial imbalance? These are not small quibbles. They are not rounding errors or instrumental glitches that can be swept under the rug. Decades of reanalysis using data from multiple independent spacecraft have shown them to be real features of our sky. They are the universe speaking to us in a language we are only just beginning to decipher. They are the subtle flaws in the symphony, the discordant notes that tell you there is a deeper, more complex melody playing underneath the one you thought you knew. So what does this mean for our grand theory, the Big Bang? Does it signal its imminent collapse? Almost certainly not. The overwhelming weight of evidence for a hot, dense beginning remains unshakable. The expansion of the universe, the abundance of light elements, and the very existence of this cosmic background radiation form a tripod of evidence so strong that it would take far more than these anomalies to topple it. Instead, what we are witnessing is something far more exciting. We are seeing the boundaries of our knowledge. We are standing at the frontier where the map reads, "Here be dragons." These anomalies are not a failure of the Big Bang theory, but a failure of its simplest iterations. They are pushing us, forcing us to refine our ideas, to question our assumptions, and to imagine a cosmos even stranger and more wonderful than before. This is how science has always advanced. Newton's laws of gravity were not wrong, they were incomplete. They worked perfectly for predicting the fall of an apple or the orbit of the moon. But they could not explain the peculiar orbit of Mercury. It took the radical genius of Einstein's general relativity, a new theory of warped space-time, to solve that small, persistent anomaly. And in doing so, Einstein did not destroy Newton's work. He encompassed it, revealing it as a brilliant approximation of a much deeper, much weirder reality. We may be living through a similar moment in the history of thought. The standard model of cosmology, like Newton's laws, is a brilliant approximation. It has carried us almost all the way back to the beginning. But these anomalies, like Mercury's strange precession, are the clues. They are the loose threads that, when pulled, may unravel our simplistic tapestry and reveal a far richer and more intricate design underneath. Perhaps the theory of inflation needs to be more complex. Maybe the process wasn't powered by a single, simple energy field, but by multiple interacting fields that could leave behind such strange, large-scale artifacts. Cosmologists are now exploring hundreds of new inflationary models, each with its own unique signature, searching for the one that not only creates a universe like ours, but one that also naturally explains why it would have a cold spot here, or an axis there. It is a search for a more sophisticated, more nuanced creation story. Or perhaps the explanation lies in something even more profound. Perhaps these are the first observational hints of a pre-Big Bang era. We have always treated the Big Bang as the ultimate beginning, a singular point in time, beyond which our laws of physics break down, beyond which we could not ask what came before. But theories like string theory and loop quantum gravity are beginning to offer us glimpses across that threshold, suggesting our Big Bang may not have been a true beginning, but a transition, a bounce from a previous contracting universe. Could these anomalies be the faint inherited scars from a cosmos that existed before our own, relics of a former reality projected onto the canvas of our infant universe? The implications are almost too vast to hold in the mind. It would mean that our universe has a memory that its birth was not an isolated event, but part of a cycle, an eternal cosmic breath of expansion and contraction. And then there is the multiverse. Once relegated to the realm of philosophy or science fiction, it has now entered the halls of mainstream theoretical physics, propelled by the mathematics of string theory and inflation. The idea that our universe is just one of countless others, each with potentially different laws of physics, is no longer seen as mere speculation, but as a plausible, almost inevitable consequence of our best theories. If the cold spot is indeed a bruise from an interuniversal collision, it transforms this abstract mathematical concept into a testable physical reality. It would be the single most profound discovery in the history of science. It would redefine our place in existence, demoting not just our planet, not just our star, but our entire universe to a single, unremarkable member of an infinite cosmic collective. It would be the ultimate Copernican revolution. This is the new, exhilarating and deeply unsettling landscape of modern cosmology. The era of easy confirmation is over. We have entered an age of profound mystery where every new observation seems to deepen the puzzle. We find ourselves in a strange land armed with a map that is incredibly accurate in its details, but whose larger continental shapes seem bizarrely and stubbornly wrong. The quest to understand these anomalies is driving the next generation of experiments. New telescopes, both on the ground in places like the high Atacama Desert and planned for space, are being designed with the express purpose of mapping this ancient light with even greater fidelity, focusing specifically on its polarization. This property of light, the orientation of its waves, holds a different set of clues, a new layer of information in the cosmic message. Within the swirling patterns of polarization, we hope to find the signature of primordial gravitational waves, ripples in space-time generated by inflation itself. Finding them would be a monumental victory for the theory. But how they are patterned across the sky could be the key that finally unlocks the mystery of the asymmetries and alignments. It might tell us if our simple model of inflation is correct, or if a far more exotic genesis is required. Ultimately, the story of these cosmic anomalies is a story about the true nature of discovery. We imagine scientific progress as a straight line, a steady march from ignorance to enlightenment, but the reality is far more human. It is a meandering path filled with wrong turns, with beautiful theories slain by ugly facts, and with moments of profound confusion that precede breathtaking leaps of insight. Progress is not made when a theory is proven right, but when it is proven to be not quite right enough. That is where the real work begins. That is where the adventure lies. These flaws in our cosmic echo are not a cause for despair. They are a gift. They are an invitation from the universe to dig deeper, to think harder, to be bolder. They are a reminder that for all we have learned, for all the incredible power of our science, we remain infants on the shore of a vast cosmic ocean, just beginning to comprehend its depths. Whether the final explanation for these strange features requires a new chapter on inflation, a radical acceptance of the multiverse, or an entirely new paradigm of physics we can barely yet conceive, one thing has become undeniably clear. The universe we inhabit is more complex, more subtle, and infinitely more surprising than our most successful theories had ever led us to believe. The simple, elegant picture is gone, replaced by a portrait of breathtaking intricacy marked by puzzles that challenge our most fundamental notions of reality. The static that Penzias and Wilson heard 50 years ago was not the end of a story. It was the beginning of an interrogation, and the universe has not yet finished its testimony. Hidden within these faint ancient patterns of light in the cold spots and the subtle alignments lies the next great revolution in our understanding of everything. The quest is no longer about confirming what we know, it is about charting what we do not. And it is in that vast, beautiful and humbling darkness that our true destiny as explorers will be found. The answers are waiting, imprinted on the oldest light in creation, challenging us to be clever enough and brave enough to finally read them.